This lecture is about understanding similarity, and we're going to take a look at how transformations can be used to determine similarity. Similar figures have the same shape, but not necessarily the same size. And we can use all types of transformations to help us to do this. One type is called a translation. And a translation, another word for that would be a slide of a figure. Another type of transformation is called a reflection. A reflection is considered a flip of a figure. A third type is called a rotation, and that is a turn or a spin of a figure. Now the last one that we're going to talk about, and it's the one that's used for similar figures, is called dilation. And that's when we enlarge or shrink a figure. Now when we're looking at similar figures like we are here, we recognize that they have the same shape. We can see two triangles, ABC and EFD. They have similar shape, but they're not necessarily the same size. We use this symbol, this little curly sign, which means similar to show when we talk about triangles that are similar. Now, what is the difference from congruence? Well, first off, congruence has a different symbol. It has an equal sign with the similar symbol on top of it, because congruence means that it's exactly equal to. So in order for two figures to be congruent, they would have to be exactly the same size. It is possible for figures to be similar and congruent, but it's not possible for two similar figures to be congruent. Now let's take a look at how we talk about sides and angles. Now angles, we talk about congruency because the angles have the exact same angle measurement. So when we look at angle A, and when we want to compare it to one of the angles on EDF, we recognize that angle A is congruent to angle D. We also recognize that angle B is congruent to angle E. And therefore that leaves angle C congruent to angle F. Now when we talk about sides, we can see the sides are not the same length. This one here, BC, happens to be 12 in length, EF happens to be 4 in length. So we can't say that they're congruent. So we'd have to say that they're similar in that they would represent the sides that would show that these figures are similar. So when we talk about AB, which is this side right here, we would talk about side DE on the smaller triangle. Now there's an easier way, instead of going back and forth between the figures, once we've labeled the angles, we know AB, there's that DE. So if we want to see side BC, we would call that EF, because that is similar to BC. And side FD would be the side that is similar to side CA. So this way we can recognize what parts are similar and what parts are congruent in similar figures. Now the big part is basically proving that figures are similar. So we'd have to record our sequence in words and what's happening. So let's kind of take a look at what's happening first of all and then go from there. We notice that AC has a length of 1, 2, 3, 4, 5. It has a length of 6. FD has a length of 2. This suggests to us that it's going to decrease by a third. Let's double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this side here measures 12, and this side here measures 4. So we can see the ratio from 12 to 4, or from 6 to 2, means that we are going to dilate it and shrink this down by 1/3. So that's important information. Another piece of information that we may want to look at is what is happening where it's located. We know we need to shrink it. We also know we need to flip it over because it's facing the wrong direction. We need to get the triangle to go the other direction, so we are going to be involved in flipping this over. Then there's probably going to be some sliding involved, some translating to get it into the right spot. So let's take a look at where it's located right now. It's located, and we'll take a look here at point C. Point C is located at -2, 1, 2, 3, 4, 5. So currently it's located at -2, -5. Now, here's the problem with this. -2, -5 is not in the right place for us to divide by 3. We're going to get fractions and improper fractions, and it would be easier if we chose points that would work for us. So if we wanted to, it'd be easier if this was actually located at -3, -6. So let's translate this and see where that would locate us. So if we were to move the triangle and put it in this location here, so now that it is -3, -6, then we can say, hey, we can take a third of that. So our first step then is going to be, we need to translate the triangle. So we're going to write translate, and we're going to use notation, which shows that the original point xy is changed. And that's what that arrow means. We're going to take the original point and change it to, and on the x, what we wanted to do is we wanted to subtract 1, so we'll put -1. And on the y, since we wanted to go down 1, we're going to put y -1. So what we're going to do is find all the locations now of our new points. So we'll take a look at this point here. 3, 4, 5, 6, 7, 8, 9. So this is going to be -9, -6. And here 3, 1, 2, 3, 4, 5, 6. This location is going to be -3, +6. So now what we're going to do is we're going to dilate our figure. So we're going to dilate it. We're going to take the original points, those ones there I put in red, and what we're going to do is we're going to shrink it. We're going to shrink it by 1/3. So we're going to take 1/3 of the x and 1/3 of the y, and it should put us in proportion. So let's go back and look at our points that we have listed, and let's try and figure out what our new points are going to be. So -3, -6 by 1/3 would be -1, -2. -9, -6 by 1/3 would be -3, -2. And -3, 6 by 1/3 would be -1, +2. So let's find those points. -1, -2, -3, -2, -1, +2. So let's get our triangle here, and I'm going to change our color so that we can kind of keep an eye on what's going on, and I'm going to shrink it down. If I can get it right on top of it. If I can get it right on top. Okay, so now that I have it right on top of the triangle, I need to note that I need to reflect it. So what I'm going to do now is we're going to reflect over the x-axis. Excuse me, the y-axis. So we're going to take our figure here, and we're going to reflect it. So that means we're flipping it over. Again, I'm going to change our color so that it doesn't get too confusing. I'll make it blue this time. And when we flip it over, since it's one away from the y-axis, this will be one away from the y-axis as well. So this is now where we're located. And we're still not there yet. So we're going to have to translate one more time so that our triangle that we've been moving around and manipulating through transformations ends up right on top of EFD. So we're going to take our original point, which is XY, and we're going to change it. What we're going to do is not move anything on the X because we don't want to go left or right, so we're going to leave the X alone. But the Y, we need to add 1. We add 1, and then we end up right on top of EFD. So by these transformations, we have just proven that these two triangles are indeed similar and proportionate.